Hello everyone, my name is Yun Hee Lee, working at KASI in Korea. Today, I'd like to introduce my recent paper published in APJ. It is for the evolution of barred galaxies. I think we are familiar with the classification of barred galaxies according to their shapes, such as strong and weak bars, namely SB and SAB. It is the typical way following the Hubble's classification. However, today I'd like to introduce another way to classify barred galaxies according to their evolutionary stage. We call them fast and slow bars. The fast bars corresponds to the early stage in their evolution, and the slow bar to the late stage. The title of this paper is Properties of Fast and Slow Bars Classified by Epicyclic Frequency Curves from Photometry of Barred Galaxies. Let's start. According to the simulation studies, bars are always formed quickly in a massive disk in the isolated system. At first, a bar rotates fast, but by the interactions with other particles in a bulge or dark matter halo, bars are deprived of their angular momentum. Then, bar slows down and grow in their length and strength in this process. Our main goal in this paper is to test this idea from observations. We utilize the epicyclic frequency curve to classify barred galaxies. Maybe you've ever seen this graph in the textbook long before. The angular velocity of a star is represented by omega. Kappa means the epicyclic frequency. When the epicyclic frequency becomes a multiple of the differences of angular velocity between stars and a bar by integers, resonance occurs. In this graph, the horizontal line shows the bar pattern speed. Therefore, as the bar pattern speed slows down, more resonances are formed. In 1994, Beard defined barred galaxies into fast, medium, and slow bars. According to his definition, bars evolve from fast bar to slow bar. So we put together 89 galaxies with measured bar pattern speed by the Tremaine and Weinberg method. This is the most reliable way to measure the bar pattern speed. It is measured from spectroscopy. And we obtained G and I band images from pan-stars. All of the images are deconvolved and deprojected. These are the formula to derive angular velocity and epicyclic frequency from the potential. For this calculation, firstly, we construct a mass map from I-band images using the mass-to-light ratio obtained from spectroscopic analysis. Here, we need the color information of galaxies. The potential map is calculated by solving the Poisson equation. To confirm our calculation is correct, we compare our photometric velocity curve with spectroscopic data from SDSS manga. They are mostly well consistent. In this way, we calculate the radial angular velocity and epicyclic frequency for each galaxy and use the bar pattern speed in previous studies. Then we can estimate all kinds of resonance locations. The right panel shows that the correlation radius from our frequency curve is well consistent with previous results from the spectroscopic data. Now, we classify 85 barred galaxies into 11 fast bars, 59 medium bars, and 8 slow bars. 5 galaxies are classified into numbered galaxies because they have a fast bar pattern speeds than the angular velocity of stars over all the disk. We can see that the evolved bars have more structures, including an inner ring and circumnuclear ring. Firstly, we investigate whether any bar properties have a correlation with the host galaxies originally. We use the bar length, strength, and the bar pattern speed as the properties of bars, and Hubble sequence and disk circular velocity as the property of the host galaxy. We found that the bar length is a little correlation with the circular velocity of a host galaxy, which is related to mass. So we can see massive galaxies usually have long bars. On the other hand, the bar strength and the bar pattern speed do not show any correlations with velocity of the host. Next, we look into the correlations between the bar properties. All of the panels show the bar pattern speed in their x-axis. First of all, the bar pattern speed is anti-correlated with all other bar properties, including correlation radius, the bar length, and the bar pattern speed. However, when we divide galaxies into fast, medium, and slow bars, the results become different. Although it is right that the correlation radius increases as the bar slows down, we cannot see any increase of bar length. We just find a little increase of the bar strength from fast to slow bars. Therefore, differently from the expectation of simulations, our analysis supports little evolution of bars. We have other studies to support the little evolution of bars. In simulations, we can find little evolution when galaxies are gas-rich or have triaxial and fast-spinning halo. In observations, Kim et al. Examined the variations of bar length and the bar strength up to g equals 1. However, the bars do not show any growth in their length and strength over the last 7 gigayears. On the other hand, barred galaxies in the simulation of Eagle and Illustrate TNG seem to be quite different from barred galaxies in observations. The gray circles show the observational data, and the color-coded diamonds indicate the simulation data. The simulation data support a rapid evolution on this domain. However, Franco et al. Investigated these simulated images in their simulation and showed that they are not the evolved bars, but short bar. Therefore, our results support little evolution about galaxies. That's all. Thank you for listening.